So the first thing I want to do is the next binary games. I try to do one of these every week if I can remember. So let's take a look at the bytes. We haven't done them before, I know, because this one is a little bit hard. All right. So there we are. So there's base 10. You have hundreds, tens, and ones, and we all know that, I think. In base 2, you use 2 instead. So for 3-bit number, you have 1s, 2s, and 4s. And for a 4-bit number, like the nibbles we did last time, you have 4 bits, and that can get you from 0 up to 15, but no further than that. So for larger, so you have 4 bits, 1s, 2s, 4s, and 8s. But for bytes, you have 8 bits, and so you have 1s, 2s, 4s, and 8s, and then 16s, 32, 64, and 128. So this 8-bit number is 128, and none of this, and 116, and 18, and none of these, and a 1. So it's this, 128, 16, 8, and 1. So that's 153, and it's pretty irritating to try to do it in your head. But this is how people learning binary start out, learning how to do it this way. And then after you learn hexadecimal, it will get easier again. But this is the bit, so let's try a few of these. I haven't got them in a Kahoot form, so I'm not going to have extra credit for it. Anyway, what do you think of this one? See if I can get my Twitch stream. Maybe I have votes up there. Oops. Now here's my Twitch stream. Okay, good. All right. Yes, that book is fun to read. Yeah. Anyway, so what do you think of this one, folks? I say 120. You think it's 108? It's 120. The reason, now I go back. I wonder if I can go back. Looks like I can't. Anyway, it was the easy way to do it. I'm cheating. I take the left 4 bits, take that nibble and multiply it by 16, and take the right nibble. That's basically what hex is. Mm-hmm. So this one here, you have 3 times 16, that's 48, plus 8, that's 56. That's an easy way. That's easier than trying to add 16 and 32, but you would get the same answer. And so here you could have 7 plus 16 plus 32, which is 48 plus 7, which is 55. And so you go. This one would be pretty annoying, although there's always shortcuts. If they were all 1, it would be 255. This is 64. So it's 255 minus 64. So that is 191, I think. 255 minus 64. Yep, I think it's 191. Yep. Anyway, there's lots of ways to do it, but you get a little practice here doing it, and that's the bytes. And there's a couple of games, one where you go forward and one where you go backward. Here's the other one. Or here, you convert that number to binary. So what do you think of this one? 131? That should be pretty easy. Yep. Any votes? This one is to do 255 minus 135. Don't think. It's not that one, it's this one. And I can tell because it's 128. Oh, it is. It's 128 plus 3, isn't it? So it's this one. We're both wrong. This is 128, and that's 3. So it's this one. How about that one?
Minus 7.
That's what I was thinking. 127 minus 6. That's how I would do it. And that's right. That's what this is. The zeros. This is this one. Somebody online got it. The middle one. This is 127 minus 6. These two numbers are turned to 0. That's 4 and 2. Good. How about that one? 26. 16 plus 10. That one. There. I got that one. Yep, the right one. Here you got it. Because this is 16 plus 10. That's 16, and I happen to know 10 is 10, 10. All right. Anyway, that's the joy of bytes. And next time we'll do hex if I can remember. And now let's talk about the two-time pad, which is, in this book, they talk about how the Russians did this. So first we'll make a one-time pad. In a one-time pad, you have a series of bytes to make the key, and then you encrypt the message. And here I'm using readable English sentences for the key, which is not really what you should do. They should really be just random letters, but in principle this will work too. And so you have the key and you have plain text. So now I just XOR it, each byte of the plain text with a byte of the key. How do you subtract 7 on bytes? Subtract 7, you subtract 4, 2, and 1. So you can do subtraction in binary, just like you could in base 10. Anyway, so this is just going to do XOR of the bytes and then print them out. So the bytes will typically become unreadable, unprintable bytes. So let me run that here. Here's the code if I clear, and I can probably make this bigger. All right, so here's that code. There's the key and the plain text, and it's going to print them out here. It's going to print out the plain text, the hex value, the key, and the hex value, and then the hex value of the encrypted thing, which is the XOR of those two, and then it's going to print out the hex encrypted stuff. So if I run it here, so here's the message, unbreakable, awesome, that's the key, 407, that's the plain text. Here's the hexadecimal and the XOR. And so this is the encrypted mess. So it's a lot like modern encryption schemes like AES. It takes readable text and turns it into random hexadecimal bytes, because it no longer is going to fit in the ASCII space in general. So that's the encrypted version of it.
So to get it back, you just XOR the key again?
Yes, since you did XOR, you just have to XOR it again. So decrypting is here, and I think I've got that ready to go. OTP2. Yeah, now I feed in the key, and here's the ciphertext from hex. Now let me clear first to make that cleaner. Okay, there. So now the only trick is I have to read in raw hex and convert it back into bytes, which is bytes.fromhex in Python. And now I just do the same thing, and now I can print out the plain text. So if I run that one, it recovers the plain text from the bytes. Good. So that's the one-time pad, and as we've said, this is essentially perfect. If nobody can find your key stream, there is no way anybody can deduce anything from just that encrypted text. And so the more important thing, though, is you can never reuse any part of the key. All right, now, if you use the same key stream twice, the whole thing is ruined. It shatters like glass. And this is why. In here, I have the key starting with the followed by a space, and both these ciphertexts were encrypted with the same key. So to break it, you just start with a guess of the key like this. Then you decrypt it. This will start and this will crypt. So then you look at what you've got. If you get any part, if you just guess a common word like the and try it in different locations, if that word appears in the key or in either of the plain texts, part of it will turn clear, those 3 bytes. So you just guess the word the, and you print the key and both of the plain texts, and you'll see something become readable. Then you guess. So now you look at this. This is you. Maybe the next thing is a space. Try putting a space here and see if it's clear. This is called the crib drag attack. It is extremely efficient, and you don't even need a computer or anything really. That's the problem. And if you use the same key for 2 messages, then you can just decrypt the whole thing quickly, deducing it, because you just go back and forth. You guess a letter or two, you guess a letter or two, you use those letters to guess a few more letters, and you just sort of crawl through the message. It is surprisingly easy.
So you guess the letter in the key?
Yes, or in either of the messages. That's why it's even more. Even if the key is just random letters, if that word appears in either of the messages, it'll work. So if you guessed a the over here.
Same key so it does decrypt the message?
Yes, so if you guess that the here, then you'll get those 3 bytes of the key correct, and then the other 3 bytes of this message will be clear. So you just guess, and as soon as part of it looks readable, then you try to guess a few more letters on each side, and the whole thing will just sort of melt like ice. You'll get a few letters, a few more letters, a few more letters, and they call it the crib drag attack. So this one here, you can, so here's one, and I forget, either a plain text, turning a plain text message as a flag. You can decrypt this one by continuing in that code, and here's a tougher one, and here's an even tougher one. And they're really not that hard at all.
Here's
Yeah?
a variation on theme, a variation on the Caesar cipher, which is just a shift. Why not take that plain text key and instead of shifting it within the alphabet, you permute?
You can do that too.
That's much more secure than a Caesar cipher.
It's no more secure, really. It's you're just going to rearrange the letters, or are you also going to change them?
I'm not going to change it. I'm just going to permute that.
Right. You can do that, but then, yeah, there are ciphers that work like that, but they're not secure. I don't know exactly what attack would work, but I know there is one that actually works that way called RC4. RC4 is very much like what you just described, and people liked it for a while until they found an attack on it. The problem is, I don't know if it applied to the one you described, but the problem with RC4 basically shuffles the characters like cards. And the problem is it turned out to be non-random. It turned out to have a slightly higher chance of creating 127 than any other byte. And therefore, if you get millions of encrypted bytes, you can do something about the key. It's not white. It's not unbiased. The output is not random. That was what was wrong with RC4. And it worked on that system you're describing.
Yeah. Well, I remember when I was a nuclear missile launch officer, we used NSA one-time pad cryptos that we had to carry and then burn them right after we used them.
Oh, good. Yeah, well, that's great. I mean, that's why. I mean, the one-time pad is perfect if you can solve the key distribution problem. But nobody can, and that's what happened to the Russians. They didn't have enough keys, so they started putting more layers of carbon paper and making more copies of the same key and using it. And then, of course, it's very insecure. But they didn't know that. They said, well, how much difference will that make? It'll probably be fine, which is what people do. And it turns out it's not fine to use the same key twice. I don't know. I think in this book they thought they did, yes. Anyway, so why do you need two messages? Well, if you'd only had one message that was encrypted with a one-time pad, there'd be no way to crack it at all, like we said before, because you could try different one-time pads and you would create every possible message, and you have no idea which one is right. If you have two messages encrypted with the same key, that's what makes it possible to crack it without knowing the key. That's what makes it possible to guess the key. All right, I'm going to stop the recording and stick around to answer any questions. I think that's enough demos.